So hi again, welcome to tutorial 3. Today we're going to talk about the multi-layer Perceptron model and show some extra, more advanced PyTorch things. So specifically we're going to remind ourselves about the fully connected layers, theoretical concept of this model, talk about activation functions. We'll implement from scratch implementation of a simple multi-layer Perceptron, showing how to do backpropagation kind of by hand, and then show a more general and more advanced implementation of this model using PyTorch and its various components. All right. Okay, so let's just do a quick reminder about the theory. So we have this hypothesis class that we saw last time. It's called the Perceptron model, where you just take the simple weighted sum of your inputs, x or feature vector, using a weight vector and apply a bias, and then use a element-wise nonlinearity. Okay, so we saw this as a perceptron model, and we saw this schematic. This is kind of the biological correlate or kind of a background for this idea of why it's called this way. It's kind of similar to the concept of a neuron in biology, where you have dendrites accepting inputs from other neurons, and some computation is happening, and then the output is carried to the next cell's dendrites through this axon. So we showed this model, and we trained the logistic regression model using the nonlinearity as the logistic function. And one limitation that we encountered, maybe implicitly, about this logistic regression model is it's actually a linear classifier. But my question here is, in what sense is it linear, since we do have a nonlinearity here? So why is this a linear classifier? Sorry? Exactly, it creates hyperplanes. Since it's a linear combination of weights, and inputs, the decision boundaries here are therefore just straight lines in 2D or hyperplanes in ND. So in that sense, it's a linear model. Now, if we say that we take this discriminant function within the linearity and say that the decision function is when this function is a constant, for example, 0, then we have this usual representation where the weights represent the orientation of the hyperplane, and the bias represents the distance of the hyperplane from the origin. And if you take a sample x, this discriminant is the signed distance from the hyperplane. You can kind of convince yourself that geometrically this happens. I gave some tips here, but basically that's the idea. You have this hyperplane represented by the w's, this discriminant function is the distance from the hyperplane. If it's positive, it's class 1. If it's negative, it's another class. Okay, but so what if our data is not linearly separable? So a hyperplane might not be good enough for all cases. Let's say we have data sets that look like that. So what do you think? Can we still use logistic regression for these kinds of data sets? Yes or no? No? Well, change the... Well, yeah, okay, so you have something similar in your homework, actually. Basically, you can if you do some kind of a fixed nonlinear transform of your features. For example, you can transform them to polynomials and have a higher dimension. So it's a linear model in a higher dimension, but you can get nonlinear decision boundaries. But then you have to choose this transformation. So how do you choose this fixed nonlinear transformation? And what if you want to learn it, actually? Maybe you want to find a transformation that can be learned from the data. So this brings us to this model, an MLP model, or multi-layer perceptron. So visually or conceptually, you can think about this model as having L layers, where we don't include the input layer. We say L, for example, this model here on the left it has 2 layers, a hidden layer and an output layer, and this model has 5 layers. Each layer is composed of multiple perceptron models. Okay? So you have multiple perceptrons, each one has a weight vector as and a bias as parameters. So formally, if we take a layer L, it operates on the output of the previous layer and applies this. So this should be similar to what we saw in the multi-class logistic regression, where we had this matrix of weights representing kind of multiple weight vectors. So that's what's happening here, since we have a weight vector for each of these perceptrons, and after we compute this transform, we get multiple outputs. Each of these has an output. Each of these perceptrons has an output, and it's forwarded to all the inputs of the next layer and so on. Okay, so this is one layer. Okay, we refer to this model as a fully connected layer because all the inputs are connected to all the outputs, and the first layer just accepts the input, for example, the features. So this red layer is just the features. Then you have a fully connected layer here and another fully connected here with different number of perceptrons or units. Okay, so given some input sample, what you compute is the composite function of all these layers. So you apply each time an affine transform, nonlinearity, then another affine transform, then another nonlinearity, and so on. You compose it. And so there's this is the model. Okay, this is the general kind of formulation you can think about. Now there's an actual theorem that proves that this model can approximate basically any function, even with just one hidden layer and one output layer. So what it means is this is actually a very powerful hypothesis class. If you think about what we saw last time, kind of the concept of the approximation error or the expressiveness of the model. So you can imagine that MLPs, if you have lots of parameters, they're very expressive. You can approximate various functions, and if you take a differentiable nonlinearity, then you have a fully differentiable expression, which means you can optimize it using gradient-based methods. Okay, and so now again, since we have a nonlinear dependency on weights and inputs, we could get decision boundaries that look like that instead of just straight lines. But now the nonlinear transformation of the features is part of the parameters that we learn. It's not fixed. Okay, so this is an example with a different number of hidden layers. You can see kind of overfitting various regions. The more you increase the layers, in this case, the fixed number of neurons each layer. So increasing just increases the number of parameters in total, and you get this overfitting. Okay, so let's talk about activation functions for a second. So the activation function is what we call the nonlinear element-wise component of this model. So like I said, it operates on the affine parts, each layer. And so one initial question is why do we need them? Why do we need these nonlinearities? Why isn't just stacking multiple layers of this MLP enough to create a powerful representation? Yeah, because you can just combine all these matrices to one matrix multiply. Easy to see that basically you won't do anything if you won't have any nonlinearities. Your model again won't be expressive, and it won't be able to create any of these kind of complex decision boundaries. Okay, and now common choices for activations functions are the logistic function, like we saw. There's also a hyperbolic tangent, which is used in many models. It's kind of a shifted and scaled version, so it's between -1 and 1. Sometimes you want that. Sometimes you want your outputs to be scaled in this range, and usually in the last layer of a model, sometimes you want this, and you can just use the tanh for that. And what's mostly used today is this ReLU, or a rectified linear unit, which is just taking the max between the value and 0. Okay, so So you have kind of a linear function for positive values and 0 otherwise. And you can note that this is not strictly differentiable, but for practical purposes, you can compute the derivative if you just separate it to different cases. So it's also called a subgradient in optimization if you took a course about that. So let's just look at how these functions look like, what these functions look like. Sorry, I skipped it. So just a quick view. We have this sigmoid, the orange one, which we saw last time. Tan h is just scaled -1 to 1, and ReLU, as you can see, it's just a linear function after 0, and before that is 0. There's also variants of ReLU where you have some kind of, it's called a leaky ReLU, where you have a small slope here. And you can see also the derivatives, for example, which I'm plotting here for these functions. You can see one of the advantages of ReLU is it has a derivative that doesn't vanish to 0, at least for the positive part. So some of the reasons people claim for using ReLUs, and in practice they're just more effective, but some of the cited reasons are the fact that they're linear in at least half the plane, so it's much easier to optimize. You don't have any vanishing effects, but they can be 0. You can get dead neurons, which means you're stuck with 0 gradients. And also they're faster to compute, but mainly they're used for practical purposes. Okay, so that's just kind of clearing the building blocks that we're going to need theoretically for the implementation part. Okay, so unless anyone has any questions, let's go to the implementation part. Yeah.
You've talked about expressiveness, and you say that we use the nonlinear function to get this expressiveness, and for example, to arrive to a polynomial function that we cannot obtain with only a linear model. But with value, how can you, for example, get a polynomial model with only linear?
I didn't say you can get a polynomial model. I said I used the polynomials as an example for a fixed feature transformation, where you can take feature x1 and x2 and multiply them, or take x1 squared. It's not necessarily the features that you get from ReLU, but ReLU is nonlinear, and the fact that it's nonlinear will give you, in the depth, it will give you decision boundaries which are not.
But we say that we can approach any function with an MLP model.
Yeah, but it's not related to any polynomial features. It's just there's a theorem that mathematically proves that if you take an MLP model with arbitrary nonlinearity, it doesn't. Then you can approximate any function. It doesn't depend on the fact that I just gave polynomials as an example for some kind of feature engineering that people do to take some fixed transformation of the features and get an optimization problem in a higher dimension.
But it's not to mention that you can approach a polynomial function, for example, with only linear model and with a combination.
You can get very complex decision boundaries. That's the point, even with ReLU. Yes.
The nonlinear function, is it something you decided before, or you try two cases in optimization?
What do you mean when you select it for the model?
When you think about
Sometimes you have considerations. Like I said, sometimes you care about, for example, the dynamic range of the output. Usually in the output layers, so you would use a softmax or a 10H in the outputs. But like I said, usually in convolutional neural networks, empirically ReLUs are found to be very effective, much more effective than other ones, specifically because they're easier to optimize. So people use them, and just usually you can select them and just forget about the other ones, at least in the inside of your network. All right. So let's start looking at some implementations. So just to change a bit, we'll look at a simple regression problem using a 2-layer MLP. But this will just show us some concepts that we showed before. And again, first step we'll do is implement everything from scratch, just using NumPy and tensor operations. So we have this, we want to learn a continuous function this time, f of x. We have our domain. So we have d in input features, and generally our target can be also not a scalar. It can be a vector valued function. And we'll use a two-layer MLP. So we have this input layer, an output layer, and just for simplicity, we just have one nonlinearity. We just say the output is not, it's raw scores. It's not, we don't compute another nonlinearity of that. If you want, you can apply, for example, a tan H or a softmax at the end, but just because we're going to compute the gradients by hand, it's easier this way. And so again, this is our model. So we have this first weights tensor, which takes our D-in features and transforms it to H features, which this is our hidden dimension. Okay, so we have this weight matrix W1 and this bias vector of also dimension H. After we have this H-dimensional intermediate hidden representation, we apply W2, which takes it from H to D out, and add this second bias, and that's it. That's our model. Okay, and just so we have an easier time, we set D out to 1. And since it's a regression problem, we'll use this most simple loss, so it's a mean squared error loss. So the pointwise loss would be this term, just a squared error between the y hat, our model's prediction, and the ground truth. So imagine you have multiple points, and you have the value of the function at all these points. And this is our estimate. So we have this pointwise loss. And we will just sum over the pointwise loss, compute its average, and have also a regularization term, which, as you can see, does not depend on the model, does not depend on the data, only on the model. So we'll take, in this case, just the norm of our weight matrices, okay? And have this lambda is just a regularization parameter, which defines how important regularization is. Yes. Mm-hmm. Yeah, we would like small weights in this case. We would like to minimize the norm. Well, you can think about, like, if you look at just as one perceptron model, the kind of scaling of the W doesn't really matter. You just care about the side of the decision function. So this is a way to kind of limit the model's capacity and ease learning. You can see, like, in the lectures when you talk about more about optimization, that, like Alex said, it's also a kind of a prior on your type of model. So it has various advantages, kind of different kinds of advantages. But basically, this is the most simple type of regularization, L2. So I'm just showing it as an example because, again, we're going to derive the gradients by hand, and this is also just easier to derive, so that's why I used it. So now we have this model, and we want to train it. So like I said, everything here is differentiable, but we need to have our derivatives of the loss with respect to these parameter tensors. So we need to calculate it, and we don't have any help now, so we're going to do it by hand. I'm going to go over it briefly. You can look at the details if you want later. But if you just rewrite our model like that, we have this intermediate step here inside that we call Z. And we have this output of this first activation, which we'll call A. Okay? And now we can derive the gradient of the loss with respect to all these intermediate values, and then get the gradient with respect to the weight tensors. Okay, so first we just take the gradient of the loss with respect to our estimate, which is just using the squared error. You can easily see that you get this term here. And then we just keep going using the chain rule. So for example, the gradient of the loss with respect to the W2 is just the gradient with respect to the y hat, and then y hat with respect to W2. So this you can see here it's easy to calculate the derivative with respect to W2 because it's just outside here, multiplying this A term. Okay, so what you get is this previous derivative times your A, which A is an intermediate step of the calculation that you had during the forward pass of this model. And then you can just keep going, okay? You need to go through this nonlinearity, this ReLU. So if you remember that ReLU has a gradient in the positive part, and you also remember that if you take for example, a gradient, I want to take the gradient of A with respect to Z. Okay, and so I have a vector, I'm taking the gradient with respect to different vectors, so I should get a matrix. Okay, but you can imagine, since it's an element-wise operation, then only, for example, Z1 affects A1. Okay, it's element-wise. So you can just kind of you get a matrix, but most of the derivatives are 0. And when Z was 0, it's also 0. So you get this kind of term, and then you just keep going. You can say that you can say it's 0, just derivative. It's a non-differentiable point. You have a point of non-continuity, but in practice, effectively, it doesn't matter. You can just say if the value of Z is greater than or equal to 0, then you can say the derivative will be 1 there, and if not, then you can say it's 0. But it actually has theoretical background. You can see that functions that look like that can be optimized over. If you have a convex function, for example, that has these discontinuities, it's enough to have subgradients for convex optimization, for example, to work. Not that this is a convex problem, but still, it's theoretically enough. Okay, so anyways, you just keep going, and you get this loss with respect to W1, and then you keep going further, and you get these losses with respect to B, to the B's. Okay, it's really simple. You can go over this yourself. It's just chain rule, and since we don't have an output nonlinearity, then it makes it even easier. And finally, for the actual weight update, what you want is to take the sample average of these losses for each of the weight vectors. Okay, and notice that I added here this regularization term. Okay, since the regularization for each of these was just lambda over 2 times the squared norm, then you get this term as a gradient of the loss with respect to each of the weights. So you have this J is either 1 or 2 because we have 2 weight matrices. Okay. So now you have something that you can actually use to do the gradient descent step. Okay. Now let's implement it. So again, for this example, we don't really care about the data. So what I did here, I defined just some parameters for our problem. So we have 64 samples, and the input dimension is 10, and the output dimension is 1, and we have 100 dimensional hidden vector. So our hidden layer is of a dimension 100. I'm creating just random data. It really doesn't matter. Just as an example, just only matters that my dimensions are correct. So I have my input features. I have D input features with n samples, and for each of these, I have one output label. But it's not it's a continuous label. It's a continuous number. It's not a class label because it's a regression problem. Okay, and now I'm just creating matrices and vectors representing my weights. So exactly like we defined, we have this W parameters tensor with which takes D in features and gives you H, and the first bias is also dimension H, and then the second weight matrix will be from H to D out, and again for the bias we have D out. Okay. By the way, when the reason I add a small number here is just as an example. Just when using ReLUs, it's a good idea to have a positive bias, so you're in the positive side of the. Usually, you initialize your model parameters with some kind of small numbers of a random distribution and give some larger positive bias, just so you can kind of kickstart the optimization. Okay, and this is the whole kind of model here. It's just raw operations on tensors. So let's look at the forward pass. We have 2 steps. We have the first step is to calculate the inner part, the first layer, and then the output layer. So in the inner layer, we have this Z, which is our data times our weights, first weights, and adding the bias. So this is the affine part, and then applying the ReLU. Okay. Basically, that's it, element-wise. And in the second part, we do the same thing again. We take our A, which is the activations from the hidden layer, apply the weights of the second layer, and add the bias of the second layer. Okay, and then we have these y hats, which is in this case 64 numbers that are model predicted, and we take the MSE relative to the ground truth. In the backward pass, I just basically implemented what you saw previously in the formulations, in the equations of the manual derivation of the gradients that I showed. I just did it step by step. So first, when I say dy hat, I mean the derivative of the loss with respect to y hat, and then I just keep going backwards. So then I have the derivative of the loss with respect to W2, and I'm using the dy hat, and so on. It's exactly like you saw in the equations, using the chain rule and going backwards until I have what I need. So what I need is the loss with respect to W2, loss with respect to B2, loss with respect to W1, and loss with respect to B1. Keep going backwards. Then I add this regularization term on the weights. Okay, so we have, if you remember, the lambda times the actual weight vector, because this is the derivative of the L2 loss. So you have this addition to the gradient. And finally, you do your gradient descent step, which is just take the gradient times the learning rate for each of these parameters and update the parameter value. When you do this, you really need to notice that the shapes should match. So since the loss is a scalar, the gradient of the loss with respect to any tensor will be the dimension of that tensor. And also otherwise, it wouldn't work, or it might work by accident due to broadcasting, but you might get bad results. So you need to kind of be careful about the weights and what exactly the ordering here. So that's what's going on here with all these transposes and stuff. Sorry? I could have done the bias trick and it would have saved me a few lines here, but just to show that you don't have to do it, you can calculate the derivative of the loss with respect to all your parameters. And also because in the second part, I'm also doing W and B, and then the gradient calculation will be automatic, and you'll see it. So it's just to be more consistent with the second part. Yes? It's a small number that prevents you taking a step that's too large, since your function is not necessarily convex. Well, it's not convex, and even if it was convex, actually, you might, if you take a step that's too large with the gradient, you might kind of miss the minimum. So you can't take too large steps, and that's why you just have to have this hyperparameter that you kind of need to. Sorry? Yeah. Okay, so that's just a very simple implementation. Just to show that its loss is actually going down. Again, I didn't try to make it optimize fast or anything. This is just an example, just to show you that you can implement everything from scratch using manual gradient derivations. That's it. Yeah, but even that, I didn't do that here. I just ran for a fixed number of epochs, and I don't have batches. So each epoch, I just take my whole data set. And like you said, yeah, I didn't really use the loss directly. I used the y hat. Yes, in this case, you're right. Okay, so now this was again a very simple implementation, just to show you core concepts that will actually, when you will be implementing more advanced models, will be happening behind the scenes for you, but it's kind of imperative to understand these concepts. So various drawbacks of this model, kind of from a technical perspective, not from the learning perspective, but technically, it's hard. It's not modular. Kind of, it's hard to. If I wanted to add layers, I would need to do the derivation again and kind of update everything that I already did. It's hard to kind of use a different kind of metric or loss. And again, since I had to do all these manual calculations and implement them by hand using just tensor operations, it's kind of error prone and hard to extend. So you'll see that in the second homework you'll implement something that solves these concerns, but from scratch, kind of doing this automatic differentiation concept for yourself. But now we'll see the PyTorch way, at least partially, to get this functionality and actually more functionality, but with actually less work and less chance of errors. So let's go to the second part. This time it's not a 2-layer MLP, it will be an n-layer MLP. Doesn't matter. Since it will be easier now, we won't really care. It will be just a parameter for us. Okay, so our usual components that we need is some data set, the model implementation, the loss function, and optimizer here. Okay, and this time our implementation will be much more modular and allow us to kind of switch the components around and change them. So let's start just with loading the data. Again, this is just for the example, so I don't really care about the data. I'm loading MNIST, so this is a classification problem. We have these 28 by 28 images. Each image has a label which represents what digit is written there. Okay. Don't really care about that, and we'll treat these images as just as a collection of features where each pixel is a feature. In the next tutorial, we'll talk about convolutional networks, and then we'll actually start talking about how to work with images. But this is just for an example. Okay, so let's talk about our model a bit. So one thing that we're going to use extensively to implement any model here is something called the module from torch.nn. This is the package that contains various kinds of building blocks for neural network layers, and it contains loss functions and activation functions. Lots of components that you use to like building blocks to build your model. So here, what we're going to use is a component called nn.linear, which is a single MLP layer. It's a fully connected layer. So it has a weight and bias. And then we'll implement our MLP model as a subclass of this class, which is nn module, which is kind of a convenience class which gives you various capabilities. For example, you have a way to register your parameters of the model so that you can expose them to optimizers. I'll show that. And you can implement forward functions. Again, I'll show that soon. So I'll explain why it's useful. Let's go into the implementation now. So first, to understand what an NN module is doing, let's look at the first very simple one, which is this fully connected layer. So I'm importing this NN module. I have this fully connected layer, which I am creating using this NN linear. So this is a module in the Torch terminology. This will be one layer of an MLP. It has 3 input features and 5 output features. Okay, and it has bias equals true, which means we have a bias vector. So let's look at what it's doing. I'm just taking a tensor here with 10 samples of 3 input features and applying this module like a function. Okay, remember that it has this magic call function which calls the forward function. So, and I'll show that in a bit. But basically, this is calling forward, and you can see that our output has 10 samples with 5 features. So we input 3 features and got 5 features as an output. Okay, so that's the first thing that's happening. And also notice that we have this grad function attribute, which suddenly appeared here. And we didn't specify anything about requiring grad for our input tensor. So why is this appearing? Any ideas? Think about last time. Yeah, exactly, because it automatically, the weight vectors inside this automatically said that they required grad, and the operation of multiplying the weights by the input created a new tensor that also requires grad, and all these tracking operations. So this is one thing that the NN modules do for you. And they have these registered parameters, which are tensors, which require grad. So let's look at that. If I take my FC, fully connected layer module, and say parameters, and I get a generator, so I convert it to a list here, then I get two things back. I get one tensor. Look at the dimensions. Okay, it's 5 by 3. So again, this is our weight matrix W, taking 3 input features and converting to 5 output features. And the second parameter is bias vector of dimension 5. Okay, makes sense? Both of them have this required grad equals true. So these were created for me when I created the fully connected layer. This is one thing the module is doing for us. Okay, let's show another thing, that we can create these custom instances of NN module and insert any arbitrary logic that we want. So for example, to show what's happening behind the scenes, let's create a fully connected layer. Let's create our own version of this FC. So I have this class, my fully connected layer. It's subclassing NN module, which gives us all this functionality like tracking parameters and stuff like that. Register them. Okay, so it's important to call this init. Otherwise, you won't get these features and you probably get errors. So again, I want to implement a fully connected layer, so I need a weight matrix and a bias vector. Okay, so let's do that. I have these in features and out features. I'm creating just a random tensor with random values with these dimensions, out and in. So it's from in to the out. I'm saying requires grad equals true for both my weights and my biases. And then I'm using this register parameter function just to give them a name. Okay. Usually you won't have to do this if you just say self dot some module equals some module. I'll show that later. Then it will automatically register it if you're putting some module here. But in this case, I'm just doing it a bit more low level. I'm creating specific tensors as my parameters, and I have to register them. So I'm giving them a name here. Okay, and look, and after that, when I do the forward pass, so I'm implementing this forward function, which will represent my forward pass, and this is what we'll call when I use the module as a function. I can access self.w. So this instance variable was created, and it holds this value. Okay, so I'm just doing the regular thing. I'm doing x times w plus b. And just to show some custom logic, I'm just multiplying it by 3. But really, you can do whatever you want. You can have any parameters you want and just say this is your custom layer or your custom module. And it can be, you can nest them. You can have a module inside a module inside a module. And you can reuse them multiple times during the forward. You can do lots of things, which we'll see. We'll take advantage of all of that stuff in the course. So now I'll instantiate my FC. Okay, this is, again, from 3 to 5. If I apply it on my demo input tensor, I get the same kind of idea, 10 by 5. Okay, but a different grad function here, which is this mul backward, since I just, for no reason, multiplied by 3. Okay, and again, if I look at my FC parameters, I can see that it's exactly like what we had before with this regular layer. I have my weights and my bias parameters. So this is a good mental model to have when you're thinking about working with these models. This is what's going on. Another thing that we can do is quickly just visualize the computation graph. Again, just to see that it's creating these this graph of operations for the forward pass of my FC. So I started with a weights matrix, and I transposed it, and then multiplied it by x, and then added b, and then multiplied it by 3. Okay, so it just really gives you a computation graph. This is what's being used when you do the backprop automatically later on when you train using AutoGrad. Okay, so this is a really simple graph, easy to understand, and it shows exactly what we did in the forward pass. Yeah.
Can you explain again the required grad? It automatically remembers the part in the chain rule that you will make.
Yes. It causes this computation graph to be saved. when you do some operation like take a tensor, multiply it by 3, and that tensor requires grad, the output also requires grad, and it's tracking that multiplication. You have this node in the graph that's inserted, which tracks that operation, and it also has lots of data stored there. It's all the data that's required for the chain rule. All right. So now we know about these modules. Let's create our MLP model. So now our MLP model is also a module, okay? And we're gonna parameterize the nonlinearity. So again, like I said last time, we had a hard time. If we wanted to change value to something else, we would have to calculate the derivatives again by hand. Now I just have this as a parameter. So again, I have this D input features. I have a list of hidden dimensions. So this is now it's a parameter. It's not a two-layer MLP anymore. It's a parameter. I have this list. And the out is the output dimensions. And I just specify the nonlinearity as a string like that. Okay, so what I'm doing here is I'm taking all my dimensions and putting them in one single list. So I can go over pairs. I'm going over pairs of dimensions. So D in, hidden 1, hidden 1, hidden 2, hidden 2, hidden 3, so on, until hidden n and D out. I'm getting these pairs, in dim, out dim. For each of these pairs, I'm creating an instance of linear. This is a fully connected layer from input to output with a bias. And then I'm taking my, for example, ReLU. Let's say nonlinear is equal to ReLU. I'm taking this class ReLU and instantiating it, and I have this linear and then ReLU. Okay, or it can be linear and something else. And I'm adding this to my growing list of layers. So now I have a growing list of layers, which will be linear ReLU, linear ReLU, linear ReLU, so on. Then I use this sequential thing. So this, what it does is gives you another module. Sequential is another module, which you give it a list of modules, and it just calls them one by one inside its forward function. Just call them one by one. So this is how I don't need to write the forward to actually chain all these linear ReLU, linear ReLU. I just use this sequential to just call them one after the other. Call this my fully connected layers. And then I have this log softmax layer, which is just taking the softmax of each row. Okay, so in the forward, I take my input, flatten it, apply all these MLP layers. Just with one call to the forward, it will call the forward of the sequential, which will call sequentially all these fully connected values until I get my raw scores, and then compute the log softmax. Okay. Let's create it, and I get a nice output printing. This is one of the things that the model does. If you print it, you get a kind of a nice output of the composition of your model. So this fully connected layers is the name of the instance variable. It was automatically registered as a parameter. Like I said, since this is a module and I'm saying self dot something, there's a hook that automatically registers it for you. So you don't need to register these parameters by hand. So now I have this FC layers, and it's a sequential of linear, tan H, linear, tan H, and so on. At the end, I have a softmax. So this is the composition of my model. I just created it using code, and you can use any arbitrary code to create any arbitrarily complex models and data flows and whatever you want to do. You just code it into this module that you're creating. Okay. So we have, let's say how many parameter tensors we have. We have 10 parameter tensors. Why 10? Any ideas? Why? 5 layers, and we have W and B. Notice that these are also layers. Tan H is a layer, but it doesn't have parameters. It's not a trainable layer. Okay, and log softmax is also a layer, but it doesn't have parameters. So we have basically 10 parameter tensors because we have 5 trainable layers, with 2 tensors each. I can also count them. So this is just counting the number of elements in each of these parameter tensors. Just for fun, to see that we have 44,000 parameters in this MLP model. And I can just easily test the forward pass, taking one input image and getting as an output one prediction for 10 class scores. Okay, since we have 10 digits in the MNIST dataset. Okay, and like you expect, the grad fn shows log softmax backward because this is the last operation that our model performed. So it kind of makes sense, and forward pass works. Let's look at how to do the loss and optimizer part using the PyTorch built-in modules. So first of all, the loss, we're going to use negative log likelihood loss. So remember, negative log likelihood is you take the log of the probability of the class that interests you. So we have this loss built in. We don't need to implement it, but it expects, if you read the documentation, it expects that it's getting log probabilities. It doesn't apply the log. So that's why we had the log softmax at the end, not a softmax, because we need log probabilities. So let's take this loss function. Let's create fake ground truth labels. I'm creating just ground truth labels in the range of integers in the range of 0 to n classes, not inclusive, so it's 0 to 9. Okay, and I'm trying out my loss. So I'm giving it, this is n by c. Yeah, n by c, n samples by c classes. And this is the class label. So it's n. And negative log likelihood is select the correct probability from here for each sample. And use the negative log probability. Okay, so we have that automatically for us using this NLL loss class here. Okay, so that's one building block, and the next building block is the optimization scheme. So, like I said, we're not going to have to calculate any gradients. What we'll do instead is, after we instantiate our model here, we'll take this class from Torch Optim SGD. This is an implementation of a regular stochastic gradient descent, and we'll give it our model parameters. So remember, this is a list, or it's not a list, it's a generator, but it's something that you can loop over to get the parameters of your model. So it just returns a sequence of tensors. So my optimizer is connected to the model only through this sequence of tensors. And these are just optimization hyperparameters like learning rate and weight decay and momentum, which you'll see later when you learn about optimization. Okay, so I've created an optimizer, and again, it's connected to my model because it has this sequence of parameter tensors. Okay, if you don't give this, or you give the wrong sequence, then it won't optimize your actual model parameters. It will optimize something else, which won't help you. Sorry? Yes, it will update them in place. So that's exactly the relation between them. So you give them the parameters, not the model itself. It doesn't care what the model looks like. For the optimizer, the model is just a list of tensors. You have to take each tensor, take the gradient, and use the gradient of that tensor to update its values. Okay? So let's look at the training loop. It will be very similar to what we did last time, but now we'll use our module MLP. Okay, so again, I'm going over epochs. Each epoch is going over the whole data set. And I'm going over batches here. And actually, I took a subset just so the training will be fast. Let's look at the training loop for a second. So this is the forward pass, taking my batch. So this can be, for example, 128 images. Okay. So this could be a 4D tensor, this X. I'm computing my class predictions for each of the input images. Computing my loss using the NNL loss built in by comparing my predicted log probabilities to my actual class labels. I'm getting this loss. This is just for plotting, for logging. And now this is the actual backward pass. So first of all, I'm running zero grad on the optimizer. Remember last time we had to zero our parameters. Now I'm telling the optimizer to zero my parameters. So why does that make sense? Think about what we saw in just a second ago. The connection between the optimizer and the model. The optimizer has a sequence of parameter tensors. It doesn't care about the model, but it can just go over them and zero the grad property of each of these tensors. So now that all of them have zero grad, I can do loss.backward. This is what is going to go back through the computation graph starting from the loss. That's why I do it backward on the loss now. Okay, on the loss, not on the y pred. I'm going backward through the loss using the computation graph and calculating using the chain rule the gradient of the loss with respect to all the intermediate tensors until I reach the leaves of this graph. And then I have my W's and my B's. This is what's going on here. And it's accumulating the gradients inside the grad property. That's why I had to zero them, so it won't accumulate from the previous batch. And then optimizer step just means take the gradients that were computed here and do the regular SGD step, which is gradient times learning rate, and then the weights minus that. So this is what's going on here. That's why, again, the optimizer doesn't need the model. It just needs the sequence of parameter tensors. Okay, and if we run that, we can see the loss is slowly going down, so it means it's working. Nice, okay. Any questions? Okay, so just to wrap up for a second, we did the same thing twice, but the second time we got a much more robust implementation, easy to change. All the components, the activation functions, the number of layers, the loss. We didn't need to derive anything manually. So we'll see you're going to use these tools more and more to implement much more complex and deeper models. Okay, but thanks.